Hello, this is Miss Moore, and today during chemistry we're going to discuss stoichiometry. Specifically today we're going to learn how to calculate mole-mole conversions. Today's essential question: given the number of moles of reactant used, how do you calculate the number of moles of products? For today's lecture, make sure you have your calculators available and just your calculators for today. Okay, let's start with a quick review of significant figures or Sig Figs. So first of all, every non-zero digit is significant. So if we had something like 3, 2, 6, 4, those are all non-zero digits, which means they're all significant. So this number has 4 Sig Figs. Okay. If we had a number like 1.76, it doesn't matter that there's a decimal there. What matters is that they are all non-zero digits. They're all significant, so we have 3 Sig Figs. Zeros between non-zero digits are significant. So if I had something like 6002, we know that the 6 and 2 are significant because they're non-zero digits, and the 2 zeros are also significant because they are between 2 non-zero digits, so this number has a total of 4 Sig Figs. All right, let's try another one of these. So how about 7 0 0 0 0 1 0 0. All right. The 7 and 1 are significant because they are non-zero digits. These 4 digits or zeros there are significant because they are between 2 non-zero digits. The 2 zeros at the end are not significant because they are not between 2 non-zero digits. So this number has a total of 6 Sig Figs. And a little bit more about zeros. Zeros before and after a decimal are significant, but not always. Only if there is a non-zero digit before them. Okay, and it doesn't need to be directly before it, just somewhere. If there is a non-zero digit somewhere before the 0 and it's before or after a decimal, it is significant. So let's try that. How about 2.00? Okay, so in this case, the 2 is significant because it's a non-zero digit. The zeros are also significant because 1, they are after a decimal, and 2, they are before a non-zero digit, which makes all of these digits significant, so 3 Sig Figs. And one more. How about 0.000100? All right. So the 1 is significant because it is a non-zero digit. This first 0 here, while it's true that it's before a decimal, there's no non-zero digit in front of it, so not significant. These 3 after the decimal are indeed after a decimal, but again, no non-zero digit in front of it, so not significant. These 2 zeros at the end are 1 after a decimal, and 2, there's a non-zero digit in front of it, so they are indeed significant. So this number has 3 Sig Figs. Okay, so that's how you count Sig Figs. So now what about Sig Figs with calculations? Remember that a calculated answer cannot be more precise or exact than the least precise measurement in your problem. So this means that the answer should be rounded to the same number of Sig Figs as the measurement with the least number of Sig Figs. So, and remember that if we're talking about multiplying and dividing, we actually count sig figs. And the one with the least number of sig figs in our problem is going to be the number of sig figs in our answer. Now, if we are adding or subtracting, we don't actually use sig figs. We count digits after the decimal. Okay, so there's a quick review on sig figs before we actually get to our stoichiometry. All right, next up, a quick review on chemical reactions. So remember that a chemical reaction involves changing substances, changing molecules. Can't really change an atom. So in a reaction, one or more substances, the things we start with, the reactants, are changed into one or more new substances, the things that we make, and we call these the products. And then we have these things called equations. Equations describe a system that rearranges atoms and bonds to make new substances. Okay, that's a really complicated way of saying that equations are what we write down on paper to represent a reaction. So why did we go over chemical reactions? Well, this thing we're actually going to be talking about now is stoichiometry. Stoichiometry is a method of chemistry that uses balanced chemical equations to predict the exact amount of a product produced from a certain amount of reactants or the amount of reactants needed to produce a certain amount of products. What we're really going to be doing this unit is mole conversions. But we're going to do these mole conversions with the goal of predicting how much reactant needed or how much product produced. And that's the whole point of stoichiometry. All right, on to mole conversions. So before we get there, we need to talk about coefficients. Remember the things that we use to balance equations? Well, the coefficients in the equation, what they're actually showing us is the number of moles of each molecule or atom being used or created in a reaction. So looking at this reaction here where we have C6H12O6, which is glucose, with oxygen producing carbon dioxide and water. And as a quick review, what kind of reaction is this? Combustion. Okay, so what these coefficients mean, so this 6 here really means we have 6 moles of oxygen and 6 moles of carbon dioxide and 6 moles of water. What about the C6H12O6? How many moles do we have of that? There's no coefficient in front. It's not going to be 0, because if we had 0 moles, we wouldn't even write it. So if there's no coefficient there, it's an invisible 1, and we have 1 mole of glucose. So again, this is really important for mole conversions. You need to remember that the coefficients really represent the number of moles of that thing. Okay, we're just about ready to start mole conversions. First, I need to introduce you to this thing called the BCA table. So what the heck? So here's a table, BCA. What does BCA stand for? B is before, C is change, and A is after. Okay, so let me kind of introduce you to this table a little bit before we actually start using it. So first of all, we usually divide the table in half, with the left side being where we fill in information about the reactants, and the right side, the information about the products. Okay, just like the equation is set up. Okay, so next let's talk about before. What do we mean by before? Well, before means, I guess I'll write it down here, before means before the reaction has happened. Okay, so this is when we're first mixing our reactants before the products start, which means how much product are we going to have before the reaction even happens? In the before area, we're not going to have any products, right? It hasn't started yet. Okay, let's jump down to the after area. After is after reaction has happened. Okay, so we're going to assume that all of the reactants are going to be used up. So now in the after area, the reactants are going to be 0, and we'll have some amount here. All right, and then last is the change area. During the change area, it's going to be, in the reactants, it's going to be how much was used. And we're using it, right? We're using it up. That is just terrible, that used. I don't know what I wrote there. How much was used. So we're using it up, which means we're going to be getting rid of some. So that means the number is going to be negative. And the change area is how much was made. And so we're adding to it, right? So these numbers are going to be positive. Okay, so that's sort of an introduction on how the table works. If you don't really get it, don't worry about it. We're going to actually use it and it'll make a lot more sense. All right, finally, how do we do this? Steps for completing mole-mole stoichiometry conversions. This is important. We're going to go through all the steps to figure out mole-mole conversions. And we're going to do that by going through a practice problem. So why don't you jot down this practice problem and then we'll go through it. So our example is how many moles of carbon dioxide would be created from 3 moles of glucose. And then we have our balanced equation. So jot that down. Okay, and then jot down a quick little BCA table. And our first step is to write out the balanced equation in your bucket table. So, or BCA table. So we're going to have C6H12O6 plus 6O2 producing 6CO2 plus 6H2O. And we'll divide this here with the left side being the reactant side and the right side being the product side. Okay, step 2, fill out the before row, keeping in mind that before means before the reaction started, which means the amount of products are going to be 0. So we know we're going to have 0 moles of CO2 and 0 moles of H2O. The starting amount of reactants given in the is given in the problem. And if there's no starting amount of reactants, and one of the reactants is the unknown. And this second part here is we're going to try that in the second problem we do. So don't worry about that part for now. Okay, so let's go back and look. What was the starting amount of reactants given? We started with 3 moles of C6H12O6. So that's going to be our starting amount. So right here. They didn't tell us how many moles of O2. So what we're going to assume, if for any reactant that they don't give us to an amount, we're going to assume that we have an excess amount, which means plenty. And we usually abbreviate that as excess, okay? So let's fill that information into our BCA table. Okay, so 3 moles of C6H12O6 and an excess amount of O2. And let me put a few more dividing lines in here. So, gosh, it'd be nice if I could draw straight. All right. So now we have filled out our before row. We're starting with 3 moles of C6H12O6, some amount in excess, more than enough O2, producing, well, we don't know at the beginning, we have no carbon dioxide and no water. Step 3, we're going to add the mole ratio to the change row, and that is the coefficient divided by the coefficient of the given. Okay, so meaning we look up at our problem up here at the top, and we have our coefficient of the given. Our given is C6H12O6, and we have a coefficient of nothing, which means a coefficient of 1. So this one is going to be 1 over 1. That's kind of messy. Let's try that again. We have 1 over 1 for our mole ratio. For the excess one, we'll have 6 over 1. For the CO2, we have 6 over 1. And for the H2O, we have 6 over 1. So all I did is take each coefficient and put it over our given coefficient, which in this case was 1. So we've added the mole ratio to the change column. Okay, step 4, determine the amount of change and add it. Again, we're still working with the change rule. So what you need to assume is that all of the reactant is used up. So the change will be the same amount as the reactant amount. The reactant's going to be negative because we're using it, right? We're getting rid of it. And the product is going to be positive because it's being made. All right, so for C6H12O6, that's our given, right? So we used negative 3 moles, which means we used negative 3 moles of O2, and we're adding negative 3 moles of CO2, and no, we're adding to that one, and we're adding 3 moles of H2O. Now what we need to do is we need to multiply all of our changes, so the negative 3s or the positive 3s, by our mole ratio. So for this first one here, 1 over 1 times negative 3 is negative 3. And 6 over 1 times negative 3 is negative 18. And 6 over 1 times positive 3 is positive 18. And 6 over 1 times positive 3 is positive 18. Okay, so we figured out how big of a change there was for each of the reactants and products. And now the last step is to sum the change row and the before row to determine the after amounts of each of the reactants and products. So we're going to take 3 minus 3, which means we have no glucose left. For this next row here, we can't really do the summing because we have absolutely no idea how much we started with. So we're going to ignore this box. And then for the carbon dioxide, we started with none. We had a change of 18 moles, so we're ending up with 18 moles. And for the water, again, we started with none. We created 18, so we have 18 moles. Okay, so there's 2 more things we need to do in this problem before we're absolutely complete. First of all, let's figure out what the question asked, remind us what the question asked us again, and 2, we need to look at Sig Figs. So let's go back and check our original question again. So it looks like they were asking us how many moles of carbon dioxide. So that's the only answer we really needed. And then for Sig Figs, our original number only had one sig fig in it, so our answer needs to have only one sig fig. So let's go back and write our final answer for moles carbon dioxide with only one sig fig. All right, so the box we're looking for is carbon dioxide. So this one right here. So 18 moles of CO2, but we only want one sig fig, right? So we want to keep the 1 and get rid of the 8, but there's no decimal there, so that 8 is going to turn the 1 into a 2. So the final answer is 20 moles, because we need to have a placeholder, right? But no decimal, so only the 2 is significant. So 20 moles carbon dioxide is our final answer. Okay, we're going to try one more problem. Please don't quit yet. The other problem is a little bit different. We're going to start with our question, a product is going to be our known. So here we go. Jot down this problem. How many moles of aluminum are needed to form 8.34 mole of Al2O3? And our balanced equation, we have 4Al, or 4 moles Al, plus 3 moles O2 produces 2 moles Al2O3. All right, let's jot down our BCA, or bucket table. And if you remember, our first step is to write out our balanced equation. So we're going to have 4Al plus 3O2 produces 2Al2O3. We'll divide between the reactants and products. And let's put some divider lines in here. All right. So what's our next step? The next step is we need to figure out the before to the best of our ability, right? This time, however, our given is not a reactant. This time our given is a product. However, products, you don't, at the before of the reaction, a product is 0, right? So this has to be 0. This is how much product was formed. So that is going to go in the after. So we know we made 8.34 moles of Al2O3. So here's the problem. How much do we start with? We don't know. How much? So we do know that they only talk about aluminum. So we know O2 is again going to be our excess, which means we can basically ignore it. This time, aluminum before is our unknown. Okay, because that's what we're trying to figure out. All right, so we've got our before row filled out. So next is our change row. And remember that first thing we need to do is make our mole ratio. And it's going to be the ratio of each of these coefficients over our known ratio, which this time is Al2O3. So for aluminum, we're going to have a ratio of 4/2. And for oxygen, we are going to have a ratio of 3/2. And for Al2O3, it's a ratio of 2/2. So again, I got those numbers from the, so that number there comes from the coefficient, and the 2 comes from the known, coefficient of the known. Okay? All right. So now we need to figure out the amount of change. This time we need to start with the product side because that's the only place we have a number. So we have 8.34. So we need to put a number in the change column here that when you add it to 0 equals 8.34. Well, that's pretty easy. That's positive 8.34, which means the same amount was used for the reactants, but used mean it's going to be negative. And this one is negative. Oh, it's kind of crowded. I hope you can read that. All right, so now we need to multiply 4 over 2 by negative 8.34, giving us, with the correct number of Sig Figs, I got 16.7. And we need to multiply 3 over 2 by 8.34. And with the correct number of Sig Figs, I got 12.5. And 2 over 2 is 1, so this one is still 8.34. And I forgot to put my signs back in, right? That's a negative and a negative. Okay, we're on to the after row. Remember that we're assuming all products get used up, so we know this is going to be 0. And this one, in theory, would be 0, but we don't actually care because it's excess. So we can ignore that guy. So now it asks you how many moles of aluminum are needed to form. So what we're actually trying to figure out is how many moles of aluminum we started with. So this time it's B plus C equals A again, but we know A. We're trying to figure out what B is. So what plus negative 16.7 equals 0? Well, that's a pretty easy math problem. It would be 16.7. And we ended up with the right number of Sig Figs. So to answer this question, how many moles of aluminum are needed to form 8.34 mole of Al2O3? Well, 16.7 moles of aluminum are needed. Okay, that's it for today. We'll talk about this a little bit more, and hopefully you'll be able to do this. Have a good one.